I will be recording the lecture again and posting it on your portal. So if you have any questions and you don't want to be recorded, please send them to me in the chat. But today's lesson, this is section 5.3. And this is a section on elasticity. I'm not using yellow this whole time, that's for sure. So elasticity has two terms, stress and strain, that we use, and I went over them in the lesson. But stress is force over area. Now, this here is cross-sectional area. Pressure is force over area, where the area is surface area. So what's the difference, right? So if I have a box, let's say it's a certain length here, the surface area is like the face of it, whatever the face is. It's all this area. The cross-sectional area is looking down the barrel of it. So if I have that box and then I have a second box next to it, right, and I increase the cross-sectional area, this area is going to increase in here. So when you're building like a deck where you'd have a 4x4 holding it up, right, holding up your deck here, whatever, that this 4x4 is going to give you much more resistance to stress, not pressure, stress. Stress happens internally. It's an internal resistance to an external force. So it's like having two things hooked together and you're pulling them apart, right? In here, these two objects are hooked, so that's where the stress occurs. Well, inside your object here are these atoms, right? Inside here, there are all these atoms, and these atoms are all connected to each other, right? So once you have stress, what you're trying to do is break these atoms apart from each other. So the more atoms you have, the less stress you're going to feel because there's going to be more resistance in there. So the greater the cross-section, the bigger the cross-section, the smaller the amount of stress for a given force. So that's what stress is. And then strain is change in length due to external force. Like when you take a piece of gum and you pull it apart, the gum changes in its length. That's strain. That's different than stress. So strain occurs, and what happens is it causes it to pull apart. So the formula for strain is epsilon over epsilon naught. Nope, that is not the formula. I am so sorry. Epsilon is the symbol for strain. I don't know what I was thinking there. Epsilon equals delta L over L naught, where L naught is your original length, and I'm getting a little sloppy here on the opening page, and this is your change in length. So that's stress and strain. And if you were to be in a machine shop or something and you were testing the material, you would create a stress strain diagram, and that shows the elasticity of the material. The elasticity is measured with a Y. This is called Young's modulus. And in your book on page 180, they give you a whole bunch of difference of elastic moduli, or Young's modulus. So that's the elasticity. So anyway, that's a little bit of background. All of these formulas go together in one formula. And this formula we'll be using to solve our problems today, but essentially it's just one formula. Y equals F delta L over A times L naught. That's our formula. I think I got that right. Make sure. I don't think I got it backwards. Sorry. My bad. Back it up. Sorry about that. The Young's modulus formula is Y equals F times L naught over A delta L. Sorry about that. So stress, strain. It's really Y equals stress over strain. So that equals F over A over delta L over L naught. So we get this out of the denominator. That's where that formula comes from. So that is our formula that we're going to use. When we're doing this formula, make sure units match. That's the number one thing you want to remember. Make sure your units match. So you can see on page 180 that Y is usually in newtons over meters squared. So you have to make sure to convert your units to newtons and meters, right? So a lot of times you'll get your change in length in millimeters and you'll get your force in kilonewtons or meganewtons or something. You've got to convert it. Also, when you're using in the chart in page 180, all Y's, oh, I'm using yellow, you can't see it. All Y's are times 10 to the 9th. So just make sure when you look and see aluminum is 70, that's 70 times 10 to the 9th. That's the number one thing. And the number two thing is cross-sectional area. So areas are cross-sectional areas. So the different cross-sectional areas, well, the area of a sphere or a circle is pi r squared. The area of a rectangle is length times width. And the area of a triangle is 1/2 base times height. So those are your cross-sectional areas there, right? If you don't like, you can write L times W, whatever, too many L's there. But those, you have to make sure that you're using the correct area formula as well. So those are the two key takeaways when you're doing these problems, is to make sure you have the right units and to make sure that you're using the correct area formula. So that's a little background. If you watch the video, you probably know that already. So we're just going to do some problems out of the book again, 3 problems, and then it's about all we got. So we're on page 189. We'll do an easy one first here. 36. Says calculate a force a piano tuner applies to stretch a steel piano wire 8 millimeters if the original wire is 0.850 millimeters in diameter and 1.3 meters long. So we're going to go back to our old way of writing down what we know. It says calculate the force of piano wire. So we're looking for force. It says it's a steel piano wire. So we're going to need to find one Young's modulus of steel. So I'll look back at the chart. Young's modulus for steel is 210 times 10 to the 9th newtons over meters squared. The steel piano wire stretches 8 millimeters. That's delta L. 8 millimeters. We got to convert that into meters. That's 8 times 10 to the minus third meters. If the wire is originally 0.85 millimeters in diameter, so the diameter is 0.850 millimeters. And it's originally 1.35 meters long, so that's L naught. So that's our given. Our goal is to find F. Our formula is Y equals F times L naught over delta L times A. We're going to cross multiply here to get F by itself. So we'll take our denominator, move it to the numerator, and take L naught and move it to the denominator. So F equals Y delta L times A over L naught. We have to find A. Well, it's a wire, so that means it's a cylinder. So the cross-sectional of a cylinder, right, you're looking down the barrel of a gun, is a circle. So we use pi r squared. Well, the diameter is 0.850 millimeters, which is 8.5 times 10 to the minus fourth meters. So that means the radius is half of that. So that would be 4.25 times 10 to the minus fourth meters. So our area is pi times 4.25 times 10 to the minus fourth squared. Now you can solve for that here, or you can put that value in up top. I don't care which one you do. I got 5.67 times 10 to the minus 7, so. Meters squared, tiny. And now we just plug in our values. F equals 210 times 10 to the 9th times delta L, which is 8 times 10 to the minus third, times L naught, which is 1.35, over, oh, not L naught, I'm sorry, times A, 5.67 times 10 to the minus 7th, over L naught, 1.35. And F equals 705 or 0.8 newtons. Was that not on the whole time I did that? Was I just talking to myself? Or could you see the whiteboard?
We could see the whiteboard. Oh, I could.
Oh, good. I didn't have the video on.
Yeah, the camera was off, but the whiteboard was fine.
Oh, good. Camera doesn't matter anyway because you can't see me. Maybe I should leave the video off all the time, just bigger screen. Or just take it all down. Did I just, oh, I just deleted the whiteboard. No, there it is. No, I just deleted the whiteboard. Huh, doggone it. So anyway, hopefully you got that before I deleted the whiteboard. The answer was 7.05 or 705.8 newtons. Does anybody have any questions on that?
What is the Y unit? I know it's the N over M squared.
Mm-hmm.
But what is Y called again? Like,
Young's modulus, or the elastic modulus.
and that's like the amount of like
That's the amount of stretchiness, how
stretch. Yeah.
easily or how difficult it is to stretch. Like something with like steel has a very high Young's modulus because it can stretch a lot without breaking. So it can withstand a lot of force before it stretches. You know what I'm saying? Like if you look at the book on page 180, bone under tension has a Y of 16 times 10 to the 9th newtons per meter squared, right? That's bone under tension. And bone under compression, the Young's modulus is equal to 9 times 10 to the 9th. So bone is much less likely to break under tension than it is under compression. Does that make sense?
Yeah.
If you think about your bones, most of the time they're breaking because you're compressing them, like your arm, not because you're pulling on it. All right, you guys at your seats, try 31. So we're going to solve this out. The lead and pencils of graphite with the Young modulus of about 1 times 10 to the 9th Newton per meter squared. Calculate the change in length of the lead, delta L. In an automatic pencil, if you tap it straight down the pencil with a force of 4 newtons, the lead is 0.5 millimeters in diameter. So we'll just go right ahead and put that into radius. So that's 5 times 10 to the minus 4th meters in diameter. So that means the radius is half that, 2.5 times 10 to the minus 4th meters. And then finally, it's 60 millimeters long. So we're looking for this force. So we use our formula again. We want to find force. So we're just going to cross multiply. And then we just plug in our values. Now the area is pi times the radius squared. Well, Mr. Manning, we're not looking for the force. We are looking for, I didn't even read. I just got all excited. Sorry about that, guys. We are not looking for the force. We're looking for delta L. And I realized that when I went to solve for delta L, and there was no delta L. So let's go back here. We're solving for delta L, so I'll cross multiply that up. Delta L equals F L naught over AY. Delta L equals 4 times, oh, that's in millimeters. We got to convert it. 1,000 millimeters is 1 meter. So that's 60 times 10 to the minus 3rd meters. Over the area, which is pi, we just did this, 2.5 times 10 to the minus 4th squared times 1 times 10 to the 9th. Delta L equals I got 1.2 times 10 to the minus 3rd meters, which is 1.2 millimeters. So it's saying, when you click out the lead in part B, is this answer reasonable? Does it seem to be consistent? Well, yeah, it's pretty reasonable. 1.2 millimeters is about, I don't know, the width of a fingertip. So that's about how far out you're pushing the lead when you're writing with a lead pencil. So, and you guys know when you're writing with a lead pencil how easily it breaks, especially 0.5 millimeter lead. Remember that 0.5 millimeter lead? This is millimeters, sorry. Right, that's the real thin pencil. We had to buy my daughter like 0.9 millimeter lead because she'd be breaking it all the time. So you can easily see that this would break. Does that make sense? You guys get that? Is there questions? Anybody have any questions? All right, we got one more to do. We're going to do number 29 on that same page. I'm going to read this with you and try to explain it to you. It says, during a circus act, one performer swings upside down, hanging from a trapeze, holding another also upside down performer by the legs. If the upward force on the lower performer is 3 times her weight, how much do the bones in her upper legs stretch? Her mass is 60 kilograms. So her mass is 60 kilograms. So let's just do a little free body diagram here. Her weight is down, so that's 60 times 9.8. That's 588 newtons. Now she's being hung by both her legs. Oops. Sometimes I bump that eraser button. And the force is going to be half of the 588. Or 294 newtons, because it's in each leg. So that's the force, 294 newtons. And it says it's 3 times. So it's 3 times that. $882 newtons. That's the force exerted when you go to solve the problem on one of her bones in her femur. All right, so give this one a try at your seats. How are we doing out there?
Change in length.
There, I unpaused the thing. Can you see it now?
Yeah. I think I'm using the right one, but I keep getting like ridiculous answers.
All right, let's give it a try. All right, so one performer upside down. We got the force. How much do the bones in our upper legs stretch? So we're looking for delta L. That's our goal. We got to get Young's modulus for bone. I think that was what, 16 times 10 to the 9th? We can see that 35 centimeters, that's her length, which is 0.35 meters. And did they give us the radius? Yeah, they give us the radius this time. That makes things nice. 1.80 times 10 to the minus second meters. I'll just convert that right off the bat. So the area then will be pi times 1.80 times 10 to the minus second squared. So we go up here to solve for y. I'm just going to move it down here because I have more room. Y equals 882 times 0.35 divided by pi times 1.80 times 10 to the minus second squared times delta L, which is what we're solving for. So we just cross multiply delta L and Y. I'm just going to erase them because I screwed up again. So this is delta L. And then Y, I'll go down here, 16 times 10 to the 9th. I got 1.89 times 10 to the minus fifth meters. So what you guys got? No? Nobody got that?
I said what I got wrong. Now. I
Not a
just
single?
yeah, I
What's
just
that?
forgot to do the area. I just put it to I just yeah, I just
I got that same thing twice. 1.90 times 10 to the minus fifth. So that's not very much. It's like 0.019 millimeters. A very small amount for your change in length of your bone. How we doing out there? Anybody get it right? Give me a thumbs up if you got that right. Good. Good. Couple of you. So that's this section, 5.3. Does anyone have any questions? All right, well, what's today? Wednesday? I won't see it till Monday. I pushed the lab back, did you see, till the 7th? So that'll give you a little extra time to get that done. I know you guys are busy.
and what did you say about the test earlier?
The test got pushed back. I'm going to push it back till the 8th.
Okay.
You'll be at home then, so your time will be a little bit less. You'll be more in front of the computer than you are now, right? All right, so if you don't have any questions and you don't need to talk to me anymore, you can